Assalamualaikum and hi, my name is Aisha Zuhaira binti Shuhaini and my matrix number is 2311515551.
Good day everyone, my name is Esther Roshni Roman and my metric number is 2311515558.
Selamat sejahtera, I am Khoi Zihal and my metric number is 231151570.
Hi, my name is Nur Afika Alia and my matrix number is 231151598.
We are from Group 5 and today we are going to present about the assignment for controller design. For question 1A, the question is asking about the difference between PI, PD, and PID controller. The first difference of each controller is their transfer function. They have different formula to construct it as shown in the table. And the second difference is their properties, where PI controller is a low-pass filter which has zero steady-state error and high frequency gain, thus contribute to less sensitivity to noise, but it has high overshoot that may cause slower transient response and low stability. But for PD controller, its properties are opposite to the PI controller. And for PID controller, it has combined both PI and PD controller properties, which has zero steady-state error, low overshoot, high stability, and faster transient response, which is the better controller. But it is the most expensive one. For question 1B, the question asks us to determine the simplest type of controller that can reduce the maximum overshoot and also steady-state error to zero. So we know that to reduce the maximum overshoot, we need to use the derivative component which is D in the controller, and to reduce the steady-state error to zero, we need to use the integral component I in the controller. Therefore, the simplest type of controller that we can choose is PID controller. For question 1C, the question asks us to design a P, PI, and PID controllers by determining the parameter using Ziegler-Nichols tuning method with a given plant GS. From the given GS, we can factorize the S out from the denominator, so it will become a plant with integral. We know that the plant with integral, we need to use the second tuning method to solve it. And before we find the parameters for the P, PI, and PID controller, we need to find the value for KCR and PCR first. And there are two methods to find the value for KCR and PCR, which is by using manual calculation of rough criterion, and the second method is by using the MATLAB. For the manual calculation, we can find out the characteristic equation for the plant, and next, we can construct the rough table. And finally, we will find that our KCR will equal to 1.92 and our PCR will equal to 1.813. By using the MATLAB, the first step is, after we run the CISO tool of the plant, we need to change the preference to 0, host, and gain. Next, we need to open up the compensator editor. And from the previous manual calculation, we already know that our KCR will equal to 1.92. So we can directly write the 1.92 into the MATLAB to check whether the value is correct or not. And after we implement the 1.92, we see that the step response will oscillate. This means that the value is correct. After we found the value for KCR, we can continue to find the value for PCR. We can smaller down the x-axis limit, so we will get the step response as shown. And the value from one peak to another peak is the value for PCR. After we found both the value for KCR and PCR, we can continue to find the value for the parameters of P, PI, and PID controller, which is KP, TI, and TD by using the formula. And after that, we can construct the transfer function for each controller. For question 1D, the question asks us to evaluate the system response after the addition of the P, PI, and PID controller. By using the MATLAB simulation, we get the three different step response graph for each P, PI, and PID controller. And the table below show the values for overshoot, steady-state error, bandwidth, and rise time for each controller and original plant. From the value above, we know that after the addition of P controller, the system response has been speed up, but the steady-state error is still higher and may increase the oscillation. And for the PI controller, the steady-state error of the system has been eliminated, which is equal to 0, but the overshoot of the system is increased due to the integral action, thus decrease the stability of the system. Well, for the PID controller, the steady-state error has been eliminated as well as the overshoot has been reduced. Thus, it will provide the faster response and better stability due to the integral and derivative actions. For question 1E, the question asks us to fine-tune the controller by using the MATLAB simulation so that the overshoot of the system is not larger than 20%. From the previous question, we already know that the overshoot after implement the PID controller is equal to 16.4%, which is larger than 20%, so that we need to fine-tune it. So, to reduce the overshoot value, we can either reduce the gain value or the real zero value. So in here, I reduce the real zero value by half, which is equal to 1.1. But we can still see that the overshoot is equal to 20.4, which is still larger than 20%. So that we can reduce the gain value KCR. So in here, I change the value for KCR into 0.32. Then we can see that the overshoot value for the system is equal to 19.9%, which is less than 20%. Then, after we get the value of the overshoot, which is less than 20%, we can export the value we get into the coding to find the parameters after tuning. And finally, we get that the value for overshoot, steady-state error, and bandwidth, as well as rise time for the PID controller after tuning. From the values we get from the MATLAB simulation, we can show that the properties of PID controller after tuning is better than the PID controller before tuning. So we can summarize that fine-tuning is a method to provide a better system response.
So for my part is question 2. Where the A question is to determine the simplest type of controller of P, PI, PD, or PID with proper justification that is quite true. So for the Roman one is to reduce the error to 0, which is the PI controller because it reduces the bandwidth and improves the cut rate. As for the Roman 2 is to speed up the transient response and also reduce the steady-state error to 0. which the answer is the ID controller because it can reduce the steady-state error and overshoot. So for question B is to design the PPI and PD controllers based on the Unicode tuning method to improve the performance of the system. To find the controllers, we first go to the step response and do the tangent line to find the values for the L and T. So from here, we can see that the L value is 0.5, while the T value is 3, minus 3.5, minus 0.5 to get 3. So after that, we need to find the values for KP, PI, and PD for each controllers. For each controllers, we have the values we have the formulas in the table for P, PI, and PD. So we just substitute the values T and L into the formula, and we get the values for the KP, PI, and PD for each P, PI, PID controllers. So for question C, to determine the transfer function of the resulting P, PI, PD, and controllers B. So the values we got on the question B, we insert into the formula. For P controller, the formula is GC equals to KB, which is 6. For PI controller, GC equals to KB 1 plus 1 over DI, which we get to 7.2 1 plus 1 over 1.67x. Second, while for the ID controller, the formula is GC equals to KB times 1 plus 1 over TI plus DDI. Second, which we get 5.4 times 1 plus 1 over S plus 0.25x. As for the D question, we evaluate the system response of the addition of the voltage PI and PD controllers respectively. So for the B controller, it reduces the time, it decreases the steady-state error, but it increases the overshoot and the oscillation. Well, this is because the B controller generates the control signal that is proportional to the current error. So for the PI controller, it improves the steady-state error by 1 degree, but reduces the PD without properly proper selection of the PD and PI. This is because the I integral accumulates the path error and adds the corrective action until the error is 0. And lastly, for the ID controller, the zero steady-state error is 0 because the ID controller improves all the negative performance as well as the control systems. So for question A, it asks for when the overshoot is larger than 20%, find the controller using the C2 and the controller to find the ID controller. So as you can see here, the overshoot is at 20%, which is 24.7%. So to overcome this, to lower the overshoot, first we go to the C2, and then we go to the tolerance to adjust the opposite to 0 gain, and we apply. After that, we go to the controller C, where we have to add integrators and 2 zeros. And then for the location, for the 0 is at -2, both of them. And then the gain, we have to change it to 1.8. After we substitute the values for the real zeros and the gain, we go to the root blockers to adjust the design. At the design requirement, we choose the percent overshoot to 20%, and then we adjust the root blockers, the dots will be inside of the triangle. After that, if the overshoot is still above the 20%, we adjust the gain until it below the 20%. So now the overshoot is 18.9. Now we have designed the ID controllers to 18.9%, which is lower than the overshoot. After that, we will export the C into the new values into the C. So for question E, it asks for when the overshoot is larger than 20%, find the controller using the C2 and the controller to find the ID controller. So as you can see here, the overshoot is at 20%, which is 24.7%. So to overcome this, to lower the overshoot, first we go to the C2, and then we go to the tolerance to adjust the opposite to 0 gain, and we apply. After that, we go to the controller C, where we have to add integrators and 2 zeros. And then for the location, for the 0 is at -2, both of them. And then the gain, we have to change it to 1.8. After we substitute the values for the real zeros and the gain, we go to the root blockers to adjust the design. At the design requirement, we choose the percent overshoot to 20%, and then we adjust the root blockers, the dots will be inside of the triangle. After that, if the overshoot is still above the 20%, we adjust the gain until it below the 20%. So now the overshoot is 18.9. Now we have designed the ID controllers to 18.9%, which is lower than the overshoot. After that, we will export the C into. So after we export the new values for the C, we can see the new step response. We can observe that the loop system shows a faster lifetime and second time compared to the original time. The steady-state error has been eliminated due to the presence of the integral action in the ID controller. Although we still have a certain amount of the overshoot, it still remains within the acceptable limit, which is under 10%. So from here, we have the ID controller introduced to 0, which improves the transfer response of the system. The control for the complex role in the host system indicates time and then response, which is when the overshoot observed in the error time. So here, the gain margin and the base margin indicates the system is stable and with sufficient openness after the tuning. So the fine tuning using the system allows the control of the system performance compared to the using the theoretical tuning methods alone.
Hi, so I'm in charge for question 3. For A, the step response of a drug delivery system is shown in the figure below. Determine the single step of control PPI, PD, or PID that is required to Roman 1 to reduce the oscillation without sacrificing the state of function response, and Roman 2 is to reduce maximum overshoot and also reduce the error to 0. For Roman 1, the answer is PD controller because the derivative D in our PD controller increases the system damping, which effectively reduces the oscillation and overshoot. Not only that, it increases fast response. Whereas for Roman 2, the answer could either be PI and PID because both controllers are capable of eliminating steady state error, but then only the derivative D is effective in reducing the maximum overshoot. So therefore, a PID controller is the most suitable choice to satisfy the requirement. So for question B, a model for a robotic surgery control system is shown below, where CS is the controller, given GS is equals to 15 over S, and bracket XY plus 2S plus Z. So for question B, Roman 1, we'll be designing a suitable controller that can reduce the maximum overshoot and also reduce steady-state error by using Ziegler-Nichols tuning method. And at the end, we'll be determining the transfer function of our proposed controller. So first of all, the suitable controller is PID because it can both reduce the maximum overshoot and also reduce the steady-state error. And secondly, PC will be using second tuning method because of the existence of our integrator. So first of all, GS will be the transfer function of GS will be turning it into a closed-loop transfer function by adding KB. So we multiply 15 by KB and we'll add 15 KB at the bottom of our transfer function. And then after that, we can get our characteristic equation that we got earlier. Now we'll be putting it into our route table. So once after putting it in, we will get this equation 20 minus 15 KB over 2 more than 0. So once after solving the equation, we'll be getting KB is less than 1.3333. So we can conclude that the sustained oscillation will occur at KB is equal to 1.3333. Now we can find the value of our KCR. KCR is also known as KB. So since we already know KB is 1.3333, now our KCR is also 1.3333. So now we will need our auxiliary equation to find our PCR is equal to 1 over F, which is equal to 2 pi over omega. Once after substituting the value in, we get 1.9869. So now referring to our second tuning table, we know that KB is equal to 0.6 KCR. So substituting the value in, we'll get KB is equal to 0.8. So we also know that TI is equal to 0.5 PCR, substituting the value in, we'll get 0.9935, and TD is equal to 0.125 PCR, substituting the value of PCR in, we'll get 0.244, and now we can put it into the equation. Now we'll be answering our question 3 in MATLAB. So to find KCR and PCR, we would be running the first part of our code. Before that, we would be substituting the characteristic equation and also the auxiliary equation into the code. Once after doing that, we'll be getting the value for KCR, which is 1.3333, and PCR is equal to 1.986, which is very similar to what we did during our manual calculation. After that, we will be running the coding for our transfer function and also our slope transfer function, which would be displayed at our command window down there. And then to find KPTI, TD, and transfer function for PID controller, we have to run the other segment of our coding. So before that, PCR equals to 1.3333 and PCR is equals to 1.986, which should be substituted into our coding. So once we run this, we'll be getting results for KP, which is equals to 0.8, TI is 0.9935, and our TD is 0.2484, which is very similar to what we got earlier. And the transfer function for our PID controller is 0.19869 in bracket S plus 2.013 power 2 divided by S. And we can also see the body plot and step response that has been plotted by MATLAB. So here we can see that there's an overshoot. So for question B, Roman 2, if the overshoot is larger than 20%, fine-tune the controller using C rule and determine the resultant parameters of the proposed controllers. Since our overshoot is more than 20%, we have to be fine-tuning it using our C rule. So first we will be running the command for our C rule and we'll be opening the control system designer here. We will change the references and we'll add the port gain and 0, and then we right click and C and open selection so that we can add the values of our PID controller. So here we'll be adding integrator and 2 real zeros, just as exactly like it was shown at our command video, the transfer function of PID controller. So the value for real 0 is negative 2.0132 for both real 0, and our gain value is 0.1987. So after adding this value, we will now check our overshoot, which remains to be at 55.4%. Now we would be right click at the root locus, click design requirements, and click new, where we change the overshoot percentage to 20. So once after doing that, we'll be getting an area where the percentage falls, right? So after that, since the percentage is still high, 55.4, now we'll be changing the values on our real 0. So from 2.0132, now we divide it into 2, so we'll be getting negative 1.007 for both. And when we check, the overshoot is still high, 22.4, so since we need 20%, we can change the value of our gain. So gain here now it shows 0.7942, so we reduce it a bit and a bit slowly, and at 0.67, we can see our percentage overshoot is 20, just like it was asked. Since our overshoot is more than 20%, we have to be fine-tuning it using our C tool. So first we will be running the command for our C tool, and we'll be opening the control system designer here. We will change the references and we'll add the port gain. Since we have fine-tuned our overshoot to 20%, now we will be exploiting our values. So at C, we'll be changing it to PID CFE, and when we run that particular segment of our code, we will be getting the value for our KPTI and PD, the new KPTI and PD for our PID controller transfer function. So not only that, the question has asked us to find the parameters as well. So I've put it to find the parameters and the frequency parameters. Since we have fine-tuned our overshoot to 20%, now we will be exploiting our values. So at C, we'll be changing it to PID CFE, and when we run that particular segment of our code, we will be getting the value for our KPTI and PD, the new KPTI and PD for our PID controller transfer function. So not only that, the question has asked us to find the parameters as well. So I've put it to find the parameters and the frequency parameters. Since we have fine-tuned so this last part of our coding is to find the body plot and step response for our closed loop transfer function, our PID closed loop transfer function, and also our fine-tuned PID transfer function. So when we run both this code, we will get the step response and also the body plot for it.
Question A, they ask you to find the suitable controller that can reduce the maximum overshoot and also can reduce a steady state error by using Ziegler-Nichols tuning method. First, for question 4A, we need to find the T and L by using MATLAB. So after we got the step response graph, we use the tangent line to find the T and L. So we find L and T, so for L is 0.115 and T is 1.485, and we substitute these two values into our PID controller. So KP is we got 15.496 and TI is 0.23 and TD is 0.06, and then we can substitute into our GCS. Okay, for our MATLAB GCS is 0.9891 in open bracket is S plus 8.7 close bracket square over S close bracket. For question B or B, they ask you if the overshoot is larger than 20%, fine-tune the controller using CISO tools. So we can find for the original plan first. So as we can see in here in coding, this is the whole coding that we can see the bot plot, the step response, the CISO tools tree, and then after that the step response G closed loop and everything in here. After we put the coding in MATLAB, we can see they're gonna give us all the value in command window, such as under overshoot, peak time, ESS, TR, TS, and percentage overshoot. So as we can see, even though the percentage is still 0%, but still the settling time is quite low and it's quite slow for the system to run. After we put our PID controller in the coding, so for L is 0.115 and T 1.6, and they're gonna give you the KPTI and TD value and our GCS function. So after we run the coding, we will get KPTI, TD, GPID, and PID GCL. And all these value we can confirm by using a manual calculation, just like we did in 4A. And just like we can see for step response, GPID, CL, and then we're gonna see the overshoot is quite high, which is 48.9 seconds, and the ESS is already good. But we can improve this by tuning this K, which is 0.891 into a small value. So this is step response for PID controller. After we tune it, we change the gain to 0.086. So we will got the overshoot 20%, and the rise time is 1.36, and the settling time is 7.31. As you can see, this is a CISO tool for PID controller before and after tuning. For the top left is before the tuning, and then the bottom right is after we tune. We can see the difference in step response.
That's all from our group.